The goals of Chapter 3 are understand how to compute the average atomic weight of an element due to isotopes. Very important to know and apply the 4 definitions of the mole, because we will talk about the mole and finally introduce it in this chapter. Be able to calculate the empirical and molecular formula of an unknown. Being able to balance chemical equations so that the law of conservation of mass is satisfied. And there will be a problem on the exam where, at least one problem, where you'll have to determine the limiting, excess, and percent yield of a chemical reaction. Before we talk about the mole, let's review our concept of an element and these 2 numbers here. First of all, taking, for example, carbon. Carbon has an atomic number of 6. 6 is the number of protons, and that is invariant. So that's something you want to keep in mind as a review. That will never change. Carbon will always have 6 protons. This number at the bottom here is the atomic mass, and it really has 3 definitions. So let's write those 3 definitions down. The first one is, it is the mass in units known as atomic mass units, 12.01 AMU. Do not forget the units, AMU, which stands for atomic mass units. The second definition of this bottom number here is the mass number, which basically is the number of protons and neutrons. So for carbon, the number of protons plus the number of neutrons equals 12.01. This is also known as the mass number. And the third equivalency for this bottom number is the number of grams per mole. So 1 mole of carbon equals 12.01 grams. Let's go back to this decimal number of 12.01, which is the mass number, protons plus neutrons. That 0.01 implies that it's not a perfect 12 for the mass of carbon. The reason why it's not a perfect, nice, round, whole number is because of isotopes. So carbon actually has 2 isotopes, a carbon-12 at 98.9% and a carbon-13 at 1.1%. Some textbooks also refer to a radioactive carbon, carbon-14. We will not talk about that. So the carbon-13 actually contributes about 1% to that 12.01, and the carbon-12 contributes about 99% to that 12.01 mass number. So how many protons, neutrons, and electrons does carbon-12 and 13 have? Well, first of all, the protons invariant will be 6. You can just refer to that in your periodic table. Electrons are going to be also 6 because carbon has no charge, no positive charge, no negative charge. The way you see it here, it's not an ion, and so it will also be 6. The neutrons vary. So this one will have, well, let's calculate that really quickly. The atomic number is 6, so 6 plus 6 will be 12. So this will have 6 neutrons. 6 plus 7 will be 13, so this will have 7 neutrons. Let's do a practice problem that involves determining the isotopes. So copper has 2 stable isotopes, a 6329 version, which has a natural abundance and appearance of about 69.17% of the time. Yet there's another version of copper, the 6529 version, which exists 30.83% of the time in nature. So we have the atomic mass of the 6329 version, and we have the atomic mass of the 6329 version. Both of these are going to go into the atomic mass of copper that you see in the periodic table. So the 6329 copper version or isotope has an atomic mass of 62.9296. So let's go ahead and write that down, 62.9296. This will exist about 69.17% of the time. So let's just go ahead and convert that fraction, which is a percentage, into a decimal. So let's move the decimal place 2 places to the left. Likewise, this 6529 isotope of carbon has this atomic weight, exists 30.83% of the time. Let's go ahead and convert that to a decimal, just divide by 100. And so the copper that you see in the periodic table is 69% of this version, 30% of this version. So let's just add these guys up as you see here. Go ahead and check that value with what you see in the periodic table. And you'll notice that it's very, very much on target, very accurate, as we say. Now let's introduce this concept of the mole. It is an SI base unit. Mole, M-O-L-E, the symbol is M-O-L. This is not the number of molecules. This is not the number of atoms. Many people get that confused. This is just its own unit. Just like meter is its own unit, kilogram is its own unit of mass. Time has its units of seconds, though you can use minutes, years for time. You can use pounds for mass. In chemistry, we find this SI base unit used tremendously and almost universally. The first definition of the mole, as we mentioned before, grams per mole. So that bottom number in many periodic tables is the number of grams that are contained in 1 mole. So 1 mole of oxygen has 16 grams of oxygen, 15.99. I usually round up. Sometimes I do 16.01. The idea is that when you're doing these calculations, you got to be kind of fast, and don't have the time to always consult a periodic table. So I just know by heart 1 mole of oxygen is 16 grams. I add the 0.01 to take into account isotopes. Well, what about 1 mole of H2O? Okay, so remember, this is going to be 2 hydrogen, so that's going to be 2 times 1.01 grams per mole plus oxygen. There's 1 of oxygen, so that's going to be about 16.01 grams per mole, and that's about 18.01 grams per mole. So don't forget to multiply the H atomic mass by 2. We only have 1 oxygen here, so 18.01, 18.02, that is the atomic mass of water. Okay, we can do this for any compound and get its mass in grams in 1 mole. Okay, mass in grams of 1 mole. 1 mole of glucose has 180.01 grams. Again, I understand I'm kind of fudging with the decimal, but sometimes you just got to do these fast. To get the units to cancel out, we flip the conversion factor to get it to moles per gram. So be able to convert grams to moles or moles to grams. The second definition of the mole has to do with this constant, Avogadro's number, 6.022 times 10 to the 23 atoms, 6.022 times 10 to the 23 molecules, and 6.22 times 10 to the 23 ions. Okay, so calcium is an ion plus 2 ions, so it's going to have 1 mole of that will have this many Avogadro's number of ions, Avogadro's number of molecules, Avogadro's number of atoms. So just look at this number, 6.022 times 10 to the 23. That is a huge number. 10 to the 23 is 1 followed by 20, or 10 followed by 23 zeros. That's a lot of atoms. Okay, that's a lot of molecules, and that's a lot of ions. That is to be expected because the whole universe is composed of atoms, molecules, and ions. Very, very small. So we would expect a lot because we're really dealing with the atomic world here. So conversion factors, 1 mole of oxygen will have Avogadro's number. 1 mole of water will have this many number of molecules of water. 1 mole of water will have this many molecules of water, not atoms, not atoms. 1 mole of water, water is a molecule, will have this many molecules. 1 mole of oxygen, oxygen is an atom, has this many number of atoms, Avogadro's number. 1 mole of glucose, glucose is a molecule composed of 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. Glucose is a molecule, so it will have Avogadro's number of molecules. Okay, so glucose is a molecule, this many molecules. Oxygen is an atom, this many atoms. 1 mole of iron will have this many atoms. 1 mole of hydrogen will have this many atoms. 1 mole of copper will have this many atoms. Finally, calcium ion, sodium ion, fluoride ion, F-, bromide ion, Br-, will have this many ions. These are your conversion factors. One thing I've seen students mess up on is they'll say 1 mole of water has 6.022 times 10 to the 23 atoms of water. Okay, no, water is not an atom, water is a molecule. Let's look at the third definition of the mole. This is what I like to call the part-whole relationship. So let's write. What does the part-whole relationship mean? Take as an example, 1 mole of glucose will have 6 moles of carbon, conversion factor. Okay, do you guys see where I'm getting that? There's 6 moles of carbon and 1 mole of glucose. So this glucose is the whole, and the part is going to be 6 moles of carbon. Likewise, a conversion factor can be 1 mole of glucose, 12 moles of hydrogen. 1 mole of glucose, 6 moles of oxygen. It's a conversion factor. Notice here the 1 mole, the whole is at the bottom. The part, the 12 moles of hydrogen, is at the top. Conversion factors you can flip. You do what you need to do in order to cancel out the units. How about this one, C3H8O? For every 1 mole of C3H8O, there's going to be 8 moles of hydrogen. That's a mistake. For every 1 mole of C3H8O, there will be 1 mole of oxygen. For every 1 mole of C3H8O, there will be 3 moles of carbon. The final definition of the mole is the coefficient of a balanced chemical equation. So in order to employ this definition of the mole, you have to balance a chemical equation. So let's balance this equation quickly here. So anytime you balance a chemical equation, you want every atom to be accounted for. So here we have the combustion of glucose in oxygen that yields CO2 plus water. Okay, so notice all the different states here, liquid, gas. This AQ state is known as aqueous, and we will study that in chapter 4. So I balance this equation without going through the pipeline. Let's just go straight to the answer and then see why this is balanced. Well, let's do a ledger. We have 6 carbons here. Again, I'm going straight to the answer. 6 carbons here. And I have 6 carbons here. So I'm balanced with my carbons. Let's look at hydrogens. I have 12 hydrogens in what is known as the reactant side. And in the product side, I have, 6 times 2? 12. So yes, I am balanced in my hydrogen side. And now, finally, let's look at oxygens. I have 6 oxygens here. 6 times 2 is 12. So 12 plus 6 is 18. I have that in my reactant side, so to speak. And in my product side, I have 6 times 2 is 12. 6 times 2 is 12. Plus 6 times 1, or 6 O's here, is 6. So 6 oxygens. 12 oxygens, 6 plus 12 is 18, and 18 oxygens on the product side, 18 oxygens on the reactant side. This is balanced. So we will learn a little bit about how to balance this to go from here to here. However, it just takes trial and error. That's how I usually tell students when I tutor them. There's no hard and fast rule other than play around with numbers. Now, the definition of the mole, the 4th definition, relationships, relationships, and relationships. For every 6 moles of oxygen that react, how many moles of CO2 are produced? 6. I can name another one. For every 1 mole of glucose that reacts, 6 moles of water are produced. 6 moles of water are produced. 1 to 6, okay, relationship, and it's a mole. 1 mole of glucose reacts with 6 moles of oxygen, as you see here in this relationship. How about this one? 1 mole of glucose gives you 6 moles of CO2, or for every 1 mole of glucose, there's 6 moles of CO2. And finally, you can do this for as many as they are in the equation. For every 6 moles of water, we have 6 moles of CO2 that are produced. Where do these numbers come from? They come from the coefficients of a balanced chemical equation. So you need to balance it, and from this balanced equation, you get these relationships. So here's our second example. We want to make sure our equation is balanced. So balance, balance, balance. Balance, balance, balance. So let's go straight to the answer here before we discuss how we balance them. So silver nitrate plus sulfuric acid gives you silver sulfate and nitric acid. Okay, so let's look at this here. How many silver is there? We have 2 Ag. And for every 2 Ag in the reactant side, we have, okay, good, we're balanced there. NO3, I'm going to use it as 1 unit. All right, so that's a little trick. Okay, instead of saying 1 nitrogen to 2 nitrogens, we can say 2 NO3. So that's 2 NO3, and then we have 2 NO3 here in the product side. All right. Again, another tip. Okay, I see SO4 as a unit, and I see SO4 as a unit as the product side. So SO4 is a polyatomic ion, SO4 sulfate, NO3 minus polyatomic ion, NO3. So 2 H's, reactant side, 2 H's, product side. Yes, this is balanced. A couple of relationships for every 2 moles of silver nitrate. We have 1 mole of silver sulfate. For every 2 moles of silver nitrate, we have 1 mole of H2SO4, and on and on and on. I'll give you one more. For every 2 moles of silver nitrate, there's 2 moles of HNO3. Let's do some problems here. Calculate the number of grams of lead in 12.4 moles of lead. So what are we being given here? We're given 12.4 moles of lead. For every 1 mole of lead, there is how many grams of lead? So let's go to our periodic table and figure out the weight of lead. 207.2 grams of lead are in 1 mole. I got that from the periodic table. One thing I want to tell you is the moles of lead and moles of lead cancel. So that's a wonderful thing. And I get an answer of 2,569 grams of lead. So if you want it in 3 sig figs, probably 2.60 times 10 to the 3. On an exam, I'll tell you. Write your answer to 2 sig figs or 3 sig figs, or alternatively, write your answer to 2 decimal places. So converting moles to grams, grams to moles is fundamental. So please learn how to do this. What is the mass in grams of 31 atoms? Atoms. So I see a lot of students get this wrong. They see atoms and then mass, which is what we're being asked to find, and then they don't know what to do. Well, what will you use? What conversion factor will you use? Okay, one of the definitions of the mole is Avogadro's number. So start with what you are given. 31 atoms of gold. 1 mole of AU has how many grams of, 1 mole of AU has how many atoms of AU? Let me repeat, 1 mole of AU has how many atoms of AU? Okay, let's go back up here. 1 mole of AU has this many atoms of AU. Avogadro's number. Finally, 1 mole of AU has 197 grams of AU. We get that from the periodic table because we want to know the mass in grams. So, this is a train. The train has 2 compartments. This compartment, which is one definition of the mole, Avogadro's number. The second compartment is the first definition of the mole that we learned, okay, the molecular weight in grams per mole. Let's do something that should be fun, canceling out units. The atoms cancel out with the atoms. Secondly, the moles of AU cancel out with the moles of AU. 1.01 times 10 to the minus 20 grams of AU. So let's look at the answer. Look at perspective here. So I want to get your mind to grasp the idea of perspective. Okay, atoms we know are small. 31 atoms, because atoms are so small, would expect to have a very small weight. So the answers sort of jive. The answers make sense. Atoms are very small. We would expect their weight to be small. This problem, calculate the number of moles of chloroform, CHCl3 and 198 grams of chloroform. So this is your classic going from grams, this is what we're given, to moles. So 1 mole of chloroform, CHCl3, has how many grams of chloroform? Okay, 1 carbon, which is about 12, 1 hydrogen, which is about 1, 3 times Cl. And looking at my periodic table, Cl is 35. So you want to add those up. If you're in a hurry, you can just say 12.01 plus 1.01 plus 3 times 35.01, and you'll get roughly the right answer. So about 118.10 grams, I rounded here, and then the grams of CHCl3 cancels out with the grams of CHCl3. So this will be 1.68 grams of chloroform. So about 3 sig figs here, so I'll just answer to 3 sig figs. For this problem, determine the molecular mass and molar mass of citric acid. How many H atoms of citric acid are there in 10.01 grams of citric acid, which has this formula. I'm sorry, the molecular mass is going to be in AMUs. The molar mass is going to be in grams per mole. So molecular mass has units of AMU. Molar mass has units of, because it's molar, mole, grams per mole. So let's figure this out. I'm not going to use the periodic table. I'm just going to go ahead and quote unquote wing it. So H is about 1, so let's do 1.01 grams per mole. 6 carbons, so 6 carbons, that's about 12.01 grams per mole. 5 hydrogens, that's, well, I could have added 5 plus 3 and multiplied it by 8, but that's okay. 5 hydrogens. The total of, we have 8 hydrogens. That's also 1.01 grams per mole, total of 8 hydrogens. 7 oxygens, so this is about 192.21 grams per mole, and that would be, call this in red here, that would be your grams per mole molar mass. The molecular mass would be 192.21 AMUs. So let's put this in blue, and that would be your molecular mass. So how many H atoms of citric acid are there in 10.01 grams of this formula? H atoms. H atoms. So what conversion factor will we use? What relationship we will use? Okay, we're going to use Avogadro's number somewhere or somehow in this. So let's go ahead and start out with what we are given. 10.01 grams of citric acid. I'm just going to go ahead and add the hydrogens here. So there is 3 hydrogens plus 5 hydrogens, 8. So I'm just going to go ahead and do that. It's perfectly legal. 10.01 grams of citric acid. And let's go ahead and convert this to mole. 1 mole of citric acid has 192.21 grams of citric acid. So that's our first conversion factor, coming from one of the first definitions of the mole. For every 1 mole of citric acid, part-whole relationship, we have 8 moles of hydrogen. For every 1 mole of hydrogen, we have 6.022 times 10 to the 23 Avogadro's atoms of hydrogens. So pretty tricky problem, very easy to slip up. That's a common error. The conversion factors are not right. So this is the right conversion factor here. For every 1 mole of citric acid, there's 8 moles of hydrogen. For every 1 mole of hydrogen, you have your Avogadro's number of atoms. Don't forget your units. I'm getting 2.50 times 10 to the 23 atoms. So again, look at perspective here. Okay, sort of magnitude. We're asked for atoms. How many atoms? Well, do you expect a lot of atoms in a certain space? Well, yeah, because atoms are just so small, and there's a ton of them. So if 1 mole has Avogadro's number of atoms, we would expect a lot of atoms. So look at your size and scale. Make sure the answer makes sense. Coming back to this problem, all of our relationships are used, for the most part. You have this relationship, which is grams per mole. We have this relationship, part over whole. And finally, we have this relationship, Avogadro's number. And finally, cancellation of units. Grams are going to cancel with grams. Moles are going to cancel with moles. This mole of H is going to cancel out with this mole of H. And we are left with atoms. That is how many atoms we are asked to find. So units-wise, everything makes sense, and we have the right relationships. So calculate the number of grams of Al and 371 grams of Al2O3. So let's start out with what we're given, 371 grams of Al2O3. So 1 mole of Al2O3 has this many grams of Al2O3, 2 times Al plus 3 times O. And we know for every 1 mole of AlO3, we have 2 moles of Al. Finally, for every 1 mole of Al, we have about 27 or so. So getting the periodic table is about 26.98. I'll just use 27.01 grams. So you can round up or you can use the values in the periodic table. The answer will be pretty close. And let's look at our units cancellation. The grams cancels out with grams. The moles cancels out with moles. This mole of Al cancels out with this mole of Al. And we're left with grams of Al, which is what the problem asks us to find. About 196 grams of Al is what I get in my calculator. Let's move on now to percent composition of an element. Take, for example, C2H6OH. This molecule is ethanol. So ethanol, major component of a lot of alcoholic beverages. Formula of ethanol is this. This is its covalent structure. Remember, it's not ionic, it's covalent. You see these single bonds everywhere. So taking a look at the composition of ethanol, we have 2 carbons, 2 times 12, divided by 46.07. That is the sum or the molecular weight of ethanol. So this percent carbon is about 52% carbon in ethanol. This is part carbon, whole ethanol. part hydrogen, 6 parts, whole ethanol. Part oxygen, there's 1 part oxygen, whole ethanol. Add all these up together, you will get 100%. So there's a part-whole relationship. You may want to memorize this, though it's rather intuitive. All this stuff has to add up to 100%. Briefly, we talked about this, the molecular empirical formula. The empirical formula is what you actually find first, and then from there you go and generate your molecular formula when you do your problem. Sometimes the molecular formula and the empirical formula are the same. Sometimes, if you can reduce it. But the way the flow goes in a particular problem is you find the empirical formula, and then from there you generate the molecular formula. This problem will illustrate that concept. So let's take a look at this practice problem here. A sample of a compound containing boron and hydrogen contains 6.44 grams of boron and 1.803 grams of H. So this formula is going to have BH something. Okay, so that's our goal, to find the formula. The molar mass of the compound is 30 grams. What is the molecular formula? And then there's a little hint here. So we know that there's 6.44 grams of boron B. So I went ahead and converted that to moles, and I got 0.596 moles of B. Let's do the same thing for hydrogen, 1.803 grams of hydrogen. Let's go ahead and convert that to moles. I got about 1.785 moles of hydrogen when I converted it to moles. So what is our formula? Our formula is B 0.596, H 1.785. Automatically, you know that's not right. We need whole number. So how will we get this to a whole number? Well, let's divide both these numbers by the lowest common denominator. The lowest common denominator here is going to be 0.596. It's also known as normalization, forcing this lowest number to 1. So I divide both numbers by 0.596, the lowest number, so that automatically gets to 1. So that's fine. And this H gets to 2.999. We want to get it to 3. Remember, always try to get to whole numbers. So BH3. And is that our answer? Well, this is what we will call the empirical formula. But the actual molecular weight is 30 grams. So let's go ahead and compute the molecular weight of this. The molecular weight of BH3, 3 hydrogens plus 1 boron, using the values in the periodic table, we're getting about 13.84 grams per mole. That's not the right formula, okay, because the compound, or this unknown, is 30 grams. So what we need to do is figure out the molecular formula. So one way to do that is to maybe just take that 30 grams and divide it by 13.84 and get the factor. So the factor I'm getting is about 2. So let's multiply this by 2. We'll get B2H6. So the molecular formula B2H6 we got from the empirical formula BH3. Let's go ahead and figure out the molecular weight of this. The molecular weight is going to be, let's calculate that. So the molecular weight of B2H6 is about 27 or 28 grams per mole, and the problem tells us that the molecular weight is 30 grams per mole. I think that's close enough to be considered correct. And the molecular formula is B2H6. The empirical formula is BH3. We figured out the correct formula of our unknown. All right, balancing chemical equations. This is something that is trial and error. There's no hard, fast, and set rule. One thing I do, if I were to condense it down to tips and tricks, though sometimes these also do not work. You want to balance your metals first. You want to balance your nonmetals second. And then go for the loners, the ones that exist by themselves, last. Okay, because if you balance these last, because they're by themselves, they don't affect any other atom in the formula. So Cl will only affect Cl. If you have NaCl, whatever number you put in front will affect the Na as well as the Cl. So balance these loners, or these last lone elements, lone atoms last. One thing I do want to mention is fractions. So this is something that throws people off. You can have fractions, but usually what we do, just like in algebra, we clear the fraction by multiplying the whole equation by the denominator. So let's do some of these problems here. You want to make an inventory. So we have reactants, which is to the left of this arrow, products, which are to the right of this arrow, and you just go make sure you have accountability. So this problem is a good problem because it tells us about fractions. So KClO3, potassium chlorate, goes to KCl plus O2. How many Ks we have? 1K, 1K here. We have 1Cl here, 1Cl here. Oxygen. Uh-oh, we have a problem here. Because you see, we don't have even numbers. Our product side, we have 2. Our reactant side, we have 3. How will we ever get them balanced? Because we can't put a number here. I can't put 2 here because that will give me 4. I can't put 3 here because that will give me 6 oxygens. So that's why you need to use fractions. So what fraction can we use? The answer is 3/2. So here I highlighted 3/2. What does that mean? So 3/2 times O2. So you see this 2 here. This 2 cancels out with that 2 in your denominator to give you 3. And that will give me the 3 oxygens to balance out my 3 oxygens in the reactant side. So this always trips people up. You use fractions when you have this odd even conundrum. Okay? So the 2 cancels, you're left with 3 on the right, 3 on the left, they're balanced. Another thing I want to mention, normally we do not, conventional wisdom is such that we do not want fractions in our equation. So we will just multiply everything out by 2, kind of like you do in algebra. 2 KClO3, 2 KCl, plus 3 oxygens. Remember, multiplying everything out by 2, the 2's cancels, we get 3O. And that is the balanced chemical equation. So let's go ahead and do a couple of more of these. I'll let you do some of these, or the rest of these as practice. Let's go over this one here. I'm going to remove the answer, and we'll go to how we got to the answer. Combustion reaction. This molecule combusts with oxygen to give you CO2 plus water. Let's do our accounts of reactants and products. So we have C, H, and O. We have 4 on the reactant side. We have 1 on the product side, H's. We have 10 on the reactant side. We have 2 on the product side, oxygens. 2 plus 2 is 4. Okay, 2 here plus 2 here is 4. Oxygens here. 2 here plus 1 here is 3. Okay, that odd number is sort of a connection. It is which means more than likely we'll probably have to employ fractions. So go ahead and let's balance the easiest to balance, the carbons. So let's balance that. It's easy. 4. So now this gives me 4. And my oxygens have now altered. So 4 times 2 is 8. 8 plus 1 is 9. So 9 oxygens. I still have an odd number. A little bit worrisome. My hydrogens stay the same at 2. What can we balance next? Hydrogens. Okay, so again, this is a trial by error sort of deal. 5 hydrogens in the water. So 5 times 2 is going to be 10. So let's make that 10. My hydrogens are balanced. Okay, this will change my oxygens. 4 times 2 is 8. 8 plus 5 is 13. So now I have 13 oxygen. How will I balance it out? Again, you must think fractions anytime you have that awkward odd number. And it's not going to be 13 halves. Why will it not be 13 halves? Well, you already have 2 here. So 2 plus 2 is 4. So from 4, how am I going to get to 13? Notice that I have 2 already isolated. So these 2 oxygens are bound to the C4H10. If I put a number here, that's going to mess up my carbons. That's going to mess up my hydrogens. So we got our loner here, oxygen. It's not 13 halves. If you do a little bit of thinking, it's going to be 11 halves. Okay? Not 13 halves, 11 halves, because we already have the 2 here that's attached to the C4H10. So 11 halves is the right answer. So this is our balanced equation. Let's try our best to avoid fractions. at all costs. This is the right answer, but the really, really right answer is to multiply this whole equation out by 2. And that is the correct answer. You can always double check your work, right? So 8 carbons, 2 times 10 is going to be 20 hydrogens. 10 times 2 is going to be 20 hydrogens. 4 oxygens plus 22 oxygens is going to be 26. 16 oxygens plus 10 oxygens is going to be 26. So doing all the math, all of these are balanced. What I'd like to tell you is that you can go ahead and just pluck out the SO4 and balance it as a unit, right? So 1 SO4 here, 1 SO4 here, 2 hydrogens here, 2 hydrogens here, 2 Hg mercury, 2 Hg mercury, 2 Cl, 2 Cl. This is already balanced. All right. So pluck out the polyatomic ion whenever you can. It makes life a little bit easy. Maybe we'll do number 8 as a final one. I'll have the answers posted on my notes, uploaded on Blackboard. Okay. Our last one, let's look at this here. So another combustion reaction. This is butane, okay, an alkane known as butane. And it burns an oxygen to give you CO2 and water. So let's do this. All right, carbons 1, 2, 3, 4. 4 carbons here, 1 carbon. Hydrogens, count them. 3 hydrogens plus 2, 5. 5 plus 2 is 7. 7 plus 3 is 10. So we got 10 hydrogens here. We only got 2 hydrogens in our product side. And oxygens, we have 2 oxygens here. And we have 2 plus 3 is 2 plus 1 is 3. So we got 3 oxygens here. Again, that odd number should strike a red flag. Perhaps we may have to employ fractions here. Let's go ahead and balance out the easier ones. Okay, what's apparent to me is that we can balance out the carbon. And what's apparent to me is that we can balance out the hydrogen. And we're all good now in terms of carbon and hydrogens. We will balance with the lone wolf last. So 4 times 2, 8. 8 plus 5 is 13. And so 13, how will we get from 2 to 13? We can't put 6 here. That will give us 12. We can't put 7 here. That will give us 14. We can use 13 halves. So 13 halves. And this 2 will cancel out with this 2, giving you 13. We can clear the fraction to get the true right answer. So we can move on to the next part. I'll let you do these the others by yourself. Look at this problem here. The NH4 is on the ammonium ion. This is part ammonium. NH4 is on the reactant side, but NH4 is nowhere on the product side. So you're going to have to balance the N's and the H's and the chromium, Cr, and the oxygens individually. On this problem here, the PO4 you can isolate out as 1 unit and isolate out the PO4 as 1 unit in the product side. So you can balance the PO4s as 1 unit. Right, a limiting reactant problem. So you will definitely encounter this on the exam. What is a limiting reactant? A limiting reactant is the reactant that gets used up first. So please recognize that the limiting reactant is a reactant. Okay, it is not going to be a product. It's not a product. So in this problem, the limiting reactant will either be Al or Fe2O3. Okay, some students on a test question, what is the limiting reactant? They'll write Fe or they'll write Al2O3, which is ridiculous because a limiting reactant is a reactant. Okay, it is not the product. So this sets the limit on how much product you can produce. How will we know how much product is produced? The limiting reactant tells us this. So if it's like you have 5 boys and 6 girls in a dance. Right? So 5 boys will dance with 5 girls, 1 is left remaining. So the boys are the limiting because they will leave out 1 girl who's the excess. So that's the idea of a limiting reactant. It's the reagent that's going to use that first. It's also important to recognize that it is going to be sets the limit on how much product is made. So that's a very important point. So let's do this practice problem here and also do some practice problems on the homeworks that are assigned. How much aluminum oxide is formed when 124 grams of aluminum reacts with 601 grams of Fe2O3? Below is the equation. So the first thing you need to do is balance, balance, balance. So step one is balanced. Okay, so this is not a balanced chemical equation. Now our equation is balanced. Now we're going to ask ourselves two questions because we have two reactants. So we're going to ask ourselves two questions. All right, so how much product Al2O3 is formed? Well, how much Al2O3 product is formed when all of the Al is used up? So that's our second question. I'll call this 2A, okay, because there's going to be a 2B. So 124 grams of Al given to us in the product. Let's go ahead and convert it to moles. Now here's a very important relationship. For every 2 moles of Al, there is 1 mole of Al2O3, aluminum oxide. For every 1 mole of Al2O3, there is so many grams of Al2O3. We have a new relationship, and that's coming from the coefficients of the balanced chemical equation. So the grams of Al canceled with the grams of Al, the moles canceled with the moles of Al, and finally the moles of Al2O3 cancels out with the moles of Al2O3. We are left with the grams of Al2O3 when all of the Al is used up. So we have 234 grams of Al2O3 product that is produced when all of the Al reactant is used up. 2A question. Now we'll do the exact same thing and ask ourselves question 2B. How much product is formed when all of the Fe2O3 reactant is used up? So that's going to be question 2B. So question 2B is asking ourselves how much product Al2O3 is produced when all the Fe2O3 reactant is used. I'll highlight this in. So the Fe2O3, we have 601 grams of Fe2O3. 601 grams of Fe2O3. We know that every 1 mole of Fe2O3 is about 159.73 grams, getting the numbers from the periodic table, times for every, this is important now, for every 1 mole of Fe2O3, go back to your balanced equation, for every 1 mole of Fe2O3, there is 1 mole of Al2O3. There's 1 mole of Al2O3. And we know that for every 1 mole of Al2O3, there's 102 grams of Al2O3. So the grams of Fe2O3 cancel with the grams of Fe2O3. The moles of Fe2O3 cancels with the moles of Fe2O3. The moles of Al2O3 cancels with the moles of Al2O3. Doing this on my calculator, get about 384 or so grams of Al2O3 are produced when all of the Fe2O3 is used up. So the question you have to ask yourself is, what is the limiting reactant then? Is it going to be the reactant that produces 383.97 grams of the product? Or is it going to be the reactant that produces 234.25 grams of the product? The limiting reactant, it sets the limit. So this is going to be your limiting reactant. So this 124 grams of Al, the aluminum, is going to be your limiting reactant. Your excess reactant is going to be Fe2O3. So now step 3 is just determine your limiting reactant, which we found out is, you see, think about it in a secondary way. 383.97 grams of Al2O3 aluminum oxide first, or will this reaction produce 234.25 grams of aluminum oxide first? Obviously, it's going to produce this 234.25 grams of aluminum oxide first, because that is when all of this is used up. Once all of this is used up, that's it. The theoretical yield is 234.25 grams of this product, Al2O3. So theoretical yield is the maximum amount that you can, right? So the maximum amount of product Al2O3 you can make is 234.25. After that, all of this limiting reactant is used up, cannot make any more. All right, so theoretical yield is an important point to remember. It comes from your limiting reagent. Limiting reagent is an important point to remember because it sets the limit of how much is made. And then Al is limiting, this has to be your excess reagent. We can also do something else. Some other problems actually ask you to go a step ahead and figure out, though it's not part of this problem, how much excess reagent is left over. So if you ever encounter that problem, here's how you do it. Remember, the limiting sets the limit on everything. It also sets the limit on how much of this excess is left over. So let's start out with our limiting, which is 124 grams of Al. For every 1 mole of Al, there's about 27.01 grams of Al. So let me look at my periodic table, and it's about 26.9, so 27.01 grams of Al. And now let's look at our balanced chemical equation sheet. The balanced chemical equation sheet tells us that for every 2 moles of Al, there is 1 mole of Fe2O3. For every 2 moles of Al, there is 1 mole of Fe2O3. And for every 1 mole of Fe2O3, there is, looking at our periodic table, there's about 159.73 grams of Fe2O3. So doing this calculation, always make sure your units cancel out. This is a great way to verify you're thinking in the right manner. So the grams cancel, moles of Al cancel out with moles of A, moles of Fe2O3 are going to cancel out with the moles of Fe2O3, and you're left with grams of Fe2O3. So I get 366.65 grams of Fe2O3. This is the amount that reacts with your Al. So remember, Al is the limiting, so it sets 124 grams of Al will react only with 366 grams of Fe2O3. That amount reacts with this amount to give you your theoretical yield of 234.25. The limiting sets the limit on everything. It sets the limit on how much you produce, your theoretical yield. Your limiting reagent also determines how much of the excess reacts. So how much is left over, how much did we start off with here? 601 grams of Fe2O3. And this is the amount that reacts with your limiting. After that, everything else is excess. So the excess left over is 601 minus 366.6. And I'm getting about 234.35 grams. So that is the excess that's left over. Okay. So when this reaction is complete, you're going to have 234 grams of product, theoretically, keyword, that's produced. And this other reactant is going to be left over. The limiting reactant obviously is all going to be used up because we already determined via stoichiometry, via the balanced chemical equation, that it is. Finally, we have something called a percentile, and the percentile is how much you actually produced. So doing math and doing all these calculations, theoretically, in theory, we produce 234.25 grams. Precipitate spills, sometimes you weigh things and it's not so accurate. There's all sorts of human error. There's also things such as systematic error. So error is its own science. The bottom line is that we, no matter how great we are, will never get to 234.25 grams. Okay? This is important in organic chemistry when you do synthesis. You always want to get close to your theoretical, but realizing we'll never get to 100% yield, again, because stuff happens. Things spill, evaporation, etc., etc. So in this problem, they tell us we got about 200 grams that is produced of this product. Well, we made 200 grams in this product, but actually, theoretically, we can make up to 234.25 grams based on our limiting reagent all being used up. So 234.25 is our theoretical. And to get into a percent, we just multiply it by 100. So I'm getting about 85.4%, and that is our percent. You'll never be over 100%. We do not create matter. We can only match our theoretical yield set by using all our limiting reagent and utilizing the stoichiometry. So you see, this is in theory based on our balanced equation and canceling out units. Stoichiometry is what all of this is called. This is in theory, hence we get the theoretical. This is reality, okay, how much we actually get when we weigh out the product. So we have one more problem here. I will post the answer to this up on Blackboard as a practice problem. If you are comfortable in understanding this problem and can do it, if you're comfortable with the previous problem I went over, if you're comfortable with problems that are assigned in your homeworks, then you should be fine with what is available or what you will encounter on the exam.